Let's begin our curve fitting series by looking at the least squares regression approach. And we're going to start off simply by looking at linear regression first. So let's say we have something that, a plot of our data that looks something like this. It's a bit all over the place. There's a number of points and they are distributed about our space. Now, if we fitted a higher order polynomial, let's say, through every single point, we may not, it wouldn't really be well suited to do that because, well, that might not be the relationship at all between these points. And remember, we're looking at data, so there's possibly quite a bit of error associated with the recordings of these, or the measurements of these points. But we can see that, visually speaking, that there is a trend here that as we move in the positive x direction, there's an increase in the y value of the associated points. So that is some type of increase, right? Well, we can fit a linear relationship to these points by looking at minimizing the residual error between this linear relationship that we can see visually and each individual point. Okay, so let's just clear this. The mathematical relationship for the visual linear plot that I just showed you is of the form y is equal to a naught plus a1x plus e. So let's just draw this on the side here. We had all of our points and we're trying to fit a line through them. Okay, we've got the x-axis and the y-axis. Okay, now each term stands for different things. So the a0 term is our y-intercept, a1 is obviously our slope, and the e is our residual error between the line and, let me just remove that, the line and each individual point. So that distance. Okay, so we need to find a criteria that will tell us the best fit of this line. That is, one strategy might be to minimize our error. So we could rewrite this as the error equal to y minus our y-intercept minus a1x. Now, if we sum up our data, so let's say we have n data points, then the sum of our errors would be sum I equals 1 to n of the error, which is equal to the sum. I'm going to leave out I equals 1 to n and just write yi minus a0 minus a1 xi. So the x and y associated with each point. Okay, so initially we want to minimize this error, but we can't really do that in its current form. So let me just demonstrate that to you. If we had a graph or a plot that looked like something like this, where we had 3 data points, if we wanted to minimize our error, which was, remember, y minus a0 minus a1x, we could fit 2 scenarios. The first is a line that goes through the data set, through all the points, because now the error is 0. But there's another possibility, and that is something else that looks like this. So here we have, well, let me draw this in a different color. Here we have a line striking the midpoint, where satisfies minimizing this error term, and we can clearly see that it's wrong. Another example would be if we had, so let's erase this, if we had 4 points, let's say in some sort of shape, and again we could fit a couple of different lines here, one connecting these 2 points and another connecting these 2 points, and it still satisfies our error term. Well, a strategy to overcome this would be to minimize the square of the errors. So that is the sum of the squares, or the residual, equals sum, and remember I'm leaving out the terms I equals 1 to n, of the errors squared. So that is the sum of yi minus a naught minus a1 xi squared. Okay, so that's handy, but we don't know what a0 and a1 are. So in order to do that, we're going to calculate the derivative of SR with respect to a0 and the derivative of SR with respect to a1. So this, the derivative with respect to a0 is equal to minus 2 sum yi minus a0 minus ai a1 xi. And the derivative with respect to a1 is equal to minus 2. Yes, that's correct. And we've got the term yi minus a0 minus a1 xi multiplied by xi. All of that summed. Now if we set these two terms to 0, we can find a relationship between our values in yi and xi in order to calculate a0 and a1. So if we do that, we end up with the following, that a1 is equal to n multiplied by the sum of xi yi minus the sum of xi yi divided by n times the sum xi squared minus the sum of xi squared. Just note that these are two very different terms. Okay, and we can then solve for a0 because it's equal to the mean, y mean, minus a1 x mean. Okay, let's try some problems.